I'm quite pleased to introduce our colloquium speaker today. Dave Levin is a PhD candidate at the University of Maryland. He's done work with several different advisors, including our own alumni, Neil Spring. And Dave works in the general distributed systems and systems community. And we're going to hear about a couple of different pieces of work having to do with peer-to-peer systems, the influence of economic incentives and economic compatibility, and a really nice, elegant piece of design about introducing just the right bit of trusted computing hardware to add interesting properties to distributed systems that didn't have them before. And with that, take it away, Dave.
Great. Thanks very much, Steve. As the internet has grown in size and use, we find ourselves interacting more and more with people who we know less and less about. And yet somehow we're expected to achieve something together. In this talk, I'm going to present some work I've been doing in designing systems without the explicit assumption of cooperation of the participants. Now, why is this an important problem? Indeed, the internet's original design was based on this assumption of cooperation of their participants, that those who are involved in the network would do whatever was necessary or sort of dictated to them by the protocols of the designers. But again, as this network has grown in size and use, we use it for just about everything under the sun, from content to commerce to entertainment. We see various other kinds of stakeholders that now have become a part of the network and who have competing interests, which are often not cooperative, not altruistic. In particular, we have selfish behavior by which a participant may attempt to gain at the potential expense of others. And we have out-and-out malicious behavior wherein an attacker may attempt to violate some aspect of the network, a correctness of some aspect of the network. So today, to build systems that can be deployable today, we have to address this full range of behavior. Now, to make this a little bit more concrete, I'd like to present two, for illustrative purposes only, examples of systems that assumed cooperation, but then had to evolve to address selfish and malicious motives that entered into the network. For a first example, let's consider routing. The Arpanet's routing protocols, as originally designed, assumed a global routing metric that everybody tried to optimize for, without regard, for instance, for whose traffic they were carrying. But as the internet has grown in size and as these various stakeholders have entered into the network, these protocols have had to evolve to allow for profit motives and for local preferences. For example, it's very uncommon for an ISP to carry traffic for which they do not get paid. And taking that example a little bit further, many ISPs set this local preference which allows traffic or which causes traffic to leave their network as early as possible to avoid having to take responsibility for transmitting it all the way across the country, for example. We also see out-and-out malicious activity in terms of routing. For example, a malicious ISP could send fake routing advertisements in order to black hole traffic and sort of absorb traffic that was destined for some other host. This isn't an isolated example. Let's take one step up in the stack and look at TCP. TCP is predicated by the fact that the end hosts will cooperate with one another. The idea is that if an end host detects that there's congestion, then they'll decrease the rate at which they send. Otherwise, we could experience catastrophic congestion collapse. But again, just like in routing, we see selfish and malicious motives enter in for which TCP had to evolve in order to address. In terms of selfishness, there's been some work by Savage and others on the so-called optimistic acknowledgement attack, where the idea is that a receiver could game the way that you acknowledge packets to try to get more than your fair share from a sender. And we see out-and-out malicious activity as well, some very well-publicized attacks, such as the Mitnick attack, which seeks to effectively hijack others' TCP traffic. So these are two examples. I'm going to present examples of some other systems as well in the remainder of my talk, where some may have assumed cooperation at first, but where selfishness and malice crept in and the systems had to evolve. We have to address this full range of behavior if we want to deploy systems with strong properties today. So I'm going to present some more systems later on in the talk, but first let's take a step back and ask ourselves, how is it that somebody who's participating in a protocol could even exhibit this kind of behavior. How could you act selfishly or maliciously if you're a participant in a protocol? And we see that really what it boils down to is misrepresenting your internal state. You still have to talk the way everybody else is talking, but you can act based on a different idea of what your internal state really is. If you think about it, there are two fundamental ways in which you can misrepresent your state. You can misrepresent it consistently, which would mean that you're also being false. If you're consistently true, then you're not misrepresenting it. So for example, I might be in a particular state A, but I tell Steve and I tell Dan, I tell everybody that I'm in state B. I'm consistent, but I'm telling a lie. Another way to do it would be to be inconsistent. And maybe I tell Tom, hey, I am in state A, which I truly am. I tell others I'm in state B, C, D. I'm inconsistent, but perhaps sometimes true. So these are the fundamental ways in which we could lie in order to try to get ahead and be selfish or malicious. But what can we do as system designers? As those of us who try to build and deploy these systems, what can we do to address this misbehavior? I'm going to talk about two different things in this talk. To address this consistent but false approach, I'm going to talk about various ways in which we can apply incentives to get participants to tell the truth. And for this, I'm going to turn to various economic-type mechanisms, in particular game theory and mechanism design, to try to provide these incentives. To handle the issue of inconsistent, but perhaps sometimes true, views of internal state, I'm going to show the design of a piece of trusted hardware that will ensure that a participant remains consistent. It's not necessarily going to show that they're true all the time, but it is going to get them to be consistent. And by the end, I'll show that by combining these two together, we can have consistent and truthful representation of state. This is also the outline of my talk. I'm going to begin by presenting incentives in the context of BitTorrent. I'm going to present our design of trusted hardware, which we call Trink. So I'm going to start off with BitTorrent. First, a quick primer. BitTorrent seeks to distribute a large file to a large set of downloaders. Now, if we were to go the centralized server approach, all the users would go to one server, and if we didn't provision that server well enough, it's going to be very slow download speeds and overrun the server, and it would be very costly to provision a server for what we might consider to be the peak crowds. Instead, what BitTorrent does is it says, put the users to work. It separates the file into multiple pieces. The users who are downloading the file, who are called Leechers, obtain pieces of the file from peers who already have the file. And those are called seeders, those peers who already have the file. They obtain pieces of the file from these seeders, and they trade these pieces with one another. Now, an interesting aspect of this is that as the demand of the system grows, as there are more and more downloaders, also the supply of the system grows, because we get more download demand, but we also are adding upload capacity by means of having these peers trade with one another. Now, how would a peer who joins the system end up beginning in all of this? That brings us to this third class of peer called a tracker, wherein if a peer joins the system, they contact the tracker, who introduces them to some set of peers, and they start trading. Now, in this talk, I'm going to focus on the downloaders, the Leechers themselves. And it's going to be useful to think of them trading these pieces of a file as if they're playing a game. And their prime objective in this game is to try to get ahead as quickly as possible, to download as quickly as possible. And our assumption is that they're going to do it in a selfish way, but also in a rational way. So given two strategies, whichever one's best, we're going to assume they're going to go with that. Just sort of match this natural evolution of what software we could expect users to download. And again, this prime objective that's going to lead us throughout this first half of this talk is they want to download the file as quickly as possible with potential disregard for what happens to everybody else. So for these Leechers, let's dig in a little bit deeper and consider the life cycle of the Leecher. What are the various stages in the game that a Leecher might play? Well, we could think of that in terms of the amount of the file that the Leecher has downloaded. At the very beginning, they have none of the file. They need to get some initial pieces so that they can start trading. They need to be bootstrapped right out of the gates. From this, they'll typically get from some other peers, as well as those seeders and those who had that. The vast majority of the download is spent in steady state. At this point, you have some of the pieces, you're able to trade with other peers, and you want to maintain a long-lived sort of relationship with that peer, a positive relationship, so that you're downloading from those who are able to give you a lot of capacity, and you want to upload to them to appeal to those kinds of peers. And then we have the final stage, which is called endgame. At this point, I only need the last few blocks, so all bets are off. If I have to lie, cheat, and steal to get those final few pieces of the file, that's fine. If you realize you hate me after the fact, that's great, because I'm off watching my movie or playing the next patch of Warcraft, for instance. So what I'm going to focus on in this talk, I've done some work on bootstrapping and on endgame and closing the loop between them so we can have proper behavior throughout. But in this talk, I'm going to focus on what constitutes the vast majority of the download, which is steady state. And if we consider what happens during steady state, there are a few different decisions that a Leecher is able to make. They have a few different local policy decisions. Again, under this prime objective of downloading as quickly as possible, their first question that they can ask is, well, with whom should I trade? I have a various set of neighbors. To which one should I send pieces of the file? And which one should I try to request pieces of the file from? And the basic idea behind this is that I'm going to want to trade with those who are going to give me the most. And this is what ends up being predicated by what's called an unchoking algorithm. This is what decides with whom a peer trades. The second question is, what pieces of the file do I trade? Once I have established who I'm trading with, what should I trade with them? In particular, what should I request from them? And what should I try to get them to request from me? So standard practice in BitTorrent is to estimate some notion of block rarity, and I want to download the rarest blocks of the file first. The idea being that way, none of the blocks will disappear from the system, and also if many people are looking for the rare blocks, I want to be the one that tries to get them. So there's sort of simultaneously a nice aspect of the system, get the rare blocks so they don't disappear, and we're not all sitting around waiting for that final piece of the file, and at the same time also selfish motivation so that I can finish and that people want what I have. There's also this aspect of, when it comes down to what pieces to trade, is what do I tell people that I have of the file to help guide them in terms of what to request from me. I'm going to demonstrate a really interesting strategy which actually might sort of surprise you. So consider just for the time being, if you're trading with some neighbors and you want them to trade with you, you want many peers to be trading with you, what should you try to tell them? How could you possibly game what you tell them, the pieces of the file you have, in order to get them to trade a little bit more with you? Oh, yes, is there a question?
Basic question, given that I'm not in operating systems, I don't believe you're really talking about people. I think they're probably some kind of processes, and I don't know whether they are independent or whether they actually all were spawned by some larger process, and what the goal would be. Are they like all trying to download something from Expedia at the same time, or what?
So let me repeat the question real quick and make sure I understand it, is that effectively these are various different processes rather than people interacting with one another. What are their motivations? Are their interests aligned, or are these different processes competing with one another? Does that capture the question? So I think you're exactly right in noticing this distinction between the user and the decisions that are going to be made in the software. In a way that's almost sort of to our benefit, because I'm assuming that these are rational decision makers, and I think we can all agree as intelligent a group as we all might be, that we're not necessarily all that rational. We might do things that aren't necessarily what would be predicated by the best, say, economic game theoretic strategy here. In terms of where their interests are aligned, the idea is that although we're all trying to download this file, we're each individually. So I might refer to it as people, and I might use people as examples, but really just think of that as the process running. That each one of us is individually trying to download as quickly as possible with potential disregard as to everyone else. So in fact, think of it as a pure peer-to-peer kind of system, which you would almost think, well, what are the competing interests in a peer-to-peer system? We all seem to be wanting the same thing. It's so that I can get ahead, and I don't necessarily care what happens to the other people's downloads. Okay? Thanks. So these are the two questions here. With whom am I going to trade, and what pieces of the file am I going to trade? And this is going to be the outline of this first half of the talk, of the BitTorrent half of the talk. So we'll start off with this question of with whom should I trade if I'm a selfish participant, if I'm trying to get ahead. And I'm going to show how to better model the way BitTorrent does it and how we've gone about improving the way BitTorrent chooses with whom to trade. So this algorithm is called an unchoker, and BitTorrent's unchoker is a round-based algorithm. What it says is that if this is the input that I get in round T, so these are the peers who uploaded to me, I now have to determine in the following round to whom I upload and how much I upload. So the way BitTorrent does this is it sorts the contributions that I received in the previous round. Let's say these peers are named A through G, and who I give to are the top 4 uploaders to me. I split my bandwidth evenly amongst them and upload to the top 4 uploaders. Now, this is a slightly simplified view of what's going on. There's also a random slot going on and these things, but for the purposes of this, it turns out this is actually a pretty accurate model. Now, this was largely understood to be what's called tit for tat. And as a result, many expected that this is not gameable. But then there were some empirical results, largely out of this group by Pytek and others, which demonstrated that, in fact, you could game this type of system. I'm going to show some ways in which you can do that. But first, let me sort of mention that this came somewhat as a surprise. Tit for tat should not be gameable. If you look in the game theoretic literature, it says that this is a very, very solid strategy to play in a repeated game. But let me explain what tit for tat is really quickly. In a repeated game, tit for tat says, I do in the current round whatever you did to me in the previous round. You treated me well, I'll treat you well. You treated me poorly, I'll treat you poorly. I do the same exact thing. Now, if you look here, it seems as though actually this doesn't really seem to be tit for tat. There are various peers, E, F, and G, who gave to me, and I gave nothing in return. A, B, C, and D gave varying amounts to me, and I gave them the same exact thing. So you could try to say that it's some approximation of tit for tat. There are many differences here that lead us to believe that actually it's really not tit for tat. And in fact, what I claim is that a better way to view this is as an auction. Indeed, BitTorrents on Choker is an auction. Now, what does it mean to be an auction? Well, auction, broadly speaking, consists of three things. It consists of bids. In this case, bids are the prior round's uploads. It consists of goods, what we're trying to bid for, which are the next round's uploads. And the final piece in an auction is simply the auction clearing mechanism, which in this case is top four. Now, to be a little bit more concrete, this happens to be a case of a all-pay auction where you don't just make the bid and promise if I win, I happen to bid, you actually pay up front. But this is a very nice way of capturing it. When you think about it like this as an auction, you see it jumps out, well, I've never heard of this top four clearing mechanism, and indeed that's where the problem starts arising. So let's consider different ways in which we could game this means of auctioning. How can we game BitTorrents auction? Well, the first thing to note, suppose that I'm peer D, D for Dave, and I decide, I'm actually willing to give much more to this peer. So let me go ahead and do that. I'm going to contribute much more because, I like what this person's giving me. Do I get something back in return? No. My bid goes up, the goods I get in return don't change whatsoever. So I say, well, I might as well conserve what I'm spending. Why? Well, because this isn't the only auction in town. There are other auctions going on as well. The more I can save at one, the more I might be able to bid in another, and I might be able to win there. So I say, okay, I'm going to decrease my bid, and of course I see that there's a certain threshold coming out of fourth place, at which point I receive nothing for my contribution. So clearly the best thing to do is to send just enough, come in fourth place, obtain something from this, minimize the amount of bid I have to do to achieve that, do no more, no less so I can conserve budget. So there's this incentive to cheat here, which is to come in last place, which is precisely what the BitTyrant client from the school, from University of Washington, demonstrated to do. And I think this sort of jumps out as sort of a nice way of capturing a way to do that when you look at it as an auction. Looking at it as an auction also gives rise to another kind of strategy. So suppose, again, I'm willing to give much, much more to this peer, but really I had no incentive to give more than just one slot. Well, if I was willing to give more, there's a way I could go ahead and do that. I could create a doppelganger. So I'm D and D prime, and I decide I'm going to take all of this contribution I was willing to give to you, and I'm going to split it in half. I'm going to split it in half, and I'm going to increase the contributions of me and my doppelganger such that we end up both coming within the top four places. So I have to come in third and fourth place in this case. And in so doing, I end up finally, at last, contributing in such a way that I'm able to get more for what I've given. So what's sort of odd here is that you have this incentive to cheat by creating symbols, and that's the only way to really be able to get more for your contribution to any one of these peers, other than just coming in last place. So we see that there's various ways in which this auction, this top four auction, isn't quite exactly what we want. How can we go about making something better? The first question to ask when we're going to apply something like mechanism design is, what's our goal? What's the fairness property that we want to get? I'd done some work early on in fairness in these types of file swarming systems with a focus towards almost bit-by-bit fairness. And the problem with this kind of approach is that you end up not giving incentive to the very high capacity peers to give as much as they can. If I'm only going to get exactly as much as I get back, then if I have more to give to the system, what's the point of giving any more? So instead we have actually what ends up being what seems like a slightly more relaxed form of fairness, but it's going to get us quite a bit further. And that's the more you give, the more you get. Now, consider the ramifications of this kind of fairness property. If I'm a high-capacity peer, and the more I give, the more I get, then I should give as much as I possibly can so I can download as quickly as possible. More people upload to the system, increases the set of resources available to the system, which should decrease the overall system download times across the whole system for all peers. Very nice fairness property if we can achieve it. Now, to try to achieve it, we're going to try to apply auction theory. And we have to do it in a practical way, a way that's compatible with the system that we're designing. Now, what does that mean? That means we have to avoid some mismatched assumptions. So there's some assumptions in economics or in auction theory that just aren't there in systems design. For instance, we don't have a central clearinghouse. We don't have, in many cases, perfect information. We have a peer-to-peer, decentralized system, and all we get to see is our local interactions with other peers. How can we build an auction based on that? Now, one other constraint that we also add to this is that we don't want to require any modifications to the wireline protocol of BitTorrent. We don't want to change precisely the messages by which they communicate. Why is that? Well, because BitTorrent is extremely popular, and we would like to see adoption of our new client, of our new kind of local policy and new auction. If we want to get that adoption, we don't want to have to require modifications to the protocol itself. So what can we do here? Well, the auction that I propose using is called the proportional share auction. So proportional share says that the blue peer is going to give to the red peer the following amount. It's the amount that the red peer gave to him in the previous round divided by the total amount that that blue peer received. Okay, so what that means is if in the previous round 25% of everything that I got came from the red peer, then I'm going to give to that peer 25% of my bandwidth. Now, that doesn't mean that his 25% and my 25% are necessarily the same thing. I could have much higher or much lower capacity. But what it does mean is that the proportions are precisely the same. Now, let's consider what happens when we look at this. Let's take a look back at the same kind of plot that we had before with BitTorrent and see how it applies with proportional share. The first thing to note is that, yes, there's a question.
Part of the naive question, I think, on the setup, you're assuming that sort of up bandwidth and down bandwidth are separate resources, so you may as well give out 100% of what you can, that would never hurt you.
Yes, so the question is, we're assuming that, it's never going to hurt you, that you're uploading as much as you possibly can. That is the assumption. So we assume that there's sort of this exogenous event or exogenous type or desire of the user where they'll state how much they're willing to upload. We didn't want to factor that kind of, because there's many different kinds of cost models, whether you have metered prices, flat rate pricing, whether or not you have multiple applications that are all competing for your uplink bandwidth. So rather than do that, we just assume that there's some capacity set by the user that we have access to. They want to download as quickly as possible, so we should be using all of it.
Yeah, and that sounds right. That seems fair. Perhaps the most interesting from an auction setting is if your upload was competing with your download.
Oh, I see. So again, to repeat the question, interesting from an auction setting that the upload would be competing with the download. The idea is, again, that we have this budget that we can totally exhaust. And so let's think about it in terms of that. But some more aspects in terms of how that might actually factor in, maybe even with different cost models, would be something I'd be interested in talking about a little bit further. But for the time being, assume that you have a budget, your upload capacity, you can and indeed should spend all of it. There's another question.
Can you say something about why the original design had, were there any constraints that forced them to say only 4 things and we give them the same amount of upload bandwidth?
Sure, so the idea behind limiting it to 4 was that the performance of having many concurrent TCP connections would end up decreasing over time, or at a certain point would start decreasing. But as I'll show in some of the results, we don't impose such a limitation, and there have been some other results as well that don't impose such a limitation and that have achieved better download times. Not to let the cat out of the bag, but really be presenting this if I did worse in terms of performance. So the first thing to note, and when we look at proportional share in terms of based on what I got in the previous round to what I give in the next round, the first thing to note is that I'm now giving a variable number of goods to however many uploaded to me, and they're unequal goods. Some get more, some get less. Now let's consider again that I'm peer D, and again I'm willing to give more, so I go ahead and I give some more. Well, as a result, what do I get back? I gave a higher proportion, so the amount I get back is also much higher compared to others. Suppose I decrease the amount I'm willing to give, well, the amount that I get back is also reflected there. So again, it has this nice property that the more you give, the more you get. The less you give, the less you get. So we achieved our fairness property. Let's throw that other attack at it, the Sybil attack. Suppose that we're all auctioning at, we're all bidding at an auction at the blue pier, and collectively everybody else had submitted a bid of 30. This is actually one of the things that's interesting. I don't really have to know what everyone else has bid, just I can even think about it just in terms of what everyone else collectively has bid. And I decide I'm willing to bid 50 at this pier, but I'm going to be really clever about it. I'm going to split it amongst 5 of my Sybils, of my doppelgangers, each one that submits a bid of 10. Well, if I do that, then the total contribution this pier received is 80, and the proportional share that each of my Sybils gets is the same, 10 over 80. We add that together, and it's precisely the same as if I would have just submitted one large bid. So in fact, it's completely Sybil-proof, and you have incentive to not launch a Sybil attack, because while you don't gain anything, you could lose by having to pay additional control message overhead. So this seems nice. PropShare has some nice local properties that the top 4 auction does not. Does it have some global properties? And so to ask this question, let's imagine that everybody else, we're in a world where everybody else is running proportional share, and we're trying to decide what I should do. And the way to think about this is to consider a PropShare curve. Okay, so the curve where x-axis is the bandwidth given, how much bandwidth I give, and the y-axis is how much bandwidth I get in return. And if we had access to exactly the amount that these peer had their bandwidth, if we had perfect information, we would see that there's a following curve, just like this. So if there's a yellow peer running a proportional share auction, there would be a curve like this, where there's a horizontal asymptote at this yellow peer's upload capacity, and the curvature of it is determined by how much other people are uploading to this peer. Now, of course, this isn't the only auction. There's multiple auctions going on, and I'm faced with the following decision. How do I maximize the amount of bandwidth I receive given a finite budget, my upload capacity? Now, if we had perfect information, imagine I had access to these curves, then the best thing to do would be to spend my entire budget to the point and split up my budget across these various curves such that the slope at each one of these points is precisely the same, and I've spent my budget. The idea being with the slope being the same is that I have no incentive to deviate at one point because I'll lose the same as if I'd moved somewhere else. Now the problem here is that while this is great, this is the best response, and notice that it might not even be proportional share as the best response. So if one of the lines had very, very low slope, I might never end up contributing something to it, even if they gave something to me. The problem here is we can't ever compute this because we don't have perfect information. We're only able to use local information. So a question came up. We said, okay, we can't compute the best response in practice. What if we played PropShare as a result to PropShare? Because there are some similarities between this best response and proportional share. For example, the blue peer is giving us the most. It's the highest up on the y-axis, and it's also the peer we're giving the most to. So there's some things that seem to be captured by PropShare. So what if we played proportional share as a response to this? So I ran some experiments where I simulated what would happen if I played best response, if I had perfect information, versus if I played proportional share with only the local information. And as it turns out, although the allocations amongst these different peers can be very, very different, the end result, the utility that you get as a result, differs negligibly between running PropShare versus running this best response. The reason being is that the differences end up being at these points of marginal return. It's a really kind of fascinating result here, which is that if everyone else is running proportional share, you should run proportional share as well. So the question is, well, does this work in practice? Okay, theory is all well and good, but we want to build the systems. I want to build the systems that I design. We want to see if they work in practice. Does this hold up in a network, in a complex network, especially as it starts competing with other peers that may not be running the same strategy? So we had two major questions in this. The first was, can we incrementally deploy proportional share? BitTorrent is remarkably, remarkably popular. If we want to make a dent in terms of the kinds of deployment we get and adoption of better, more fair strategies, we figure it has to be incrementally deployable so that more and more users can slowly add to this. So to answer this question, we ran experiments on live downloads, on live existing swarms that compete with other BitTorrent peers. The other question is, well, what would happen as more people started adopting proportional share? So to understand that, to see what would happen as the network evolves to being all prop share, we ran some experiments on controlled populations in the context of Planet Lab. So first, live downloads. The question is, how does PropShare fare in a swarm consisting of mostly, or we can pretty much assume all, BitTorrent top 4 peers? So here's the experiment that we ran. We started 3 peers simultaneously from the University of Maryland network, BitTorrent as our baseline, BitTyrant to see, which explicitly games the BitTorrent protocol, and our PropShare client. And I just want to point out that PropShare, in this case, actually in all cases, the full implementation of it was oblivious to whatever protocols other people are running, to whatever, whether they're top 4, BitTyrant, PropShare, no matter what, we just run PropShare as a response to everything. So what would we expect to happen? Well, we'd expect certainly BitTyrant to come in to do the best. They're the one explicitly gaming the protocol. It's not even necessarily clear what might happen with PropShare, so let's take a look at the result. I ran this on 21 different torrents, and here the x-axis is just simply sorted by torrent ID. The y-axis here is the fraction of download time to that of BitTorrents, to that of our baseline. So basically, any value less than 1 means we perform better than BitTorrent. Anything greater means we perform worse than BitTorrent. And what we see is that BitTyrant, which is explicitly gaming the BitTorrent protocol, and PropShare perform comparably. Now, this is actually kind of a surprising result here, but if you think about it, what it boils down to is that PropShare is spreading its contribution across multiple peers, which has been demonstrated to have improvements in terms of download, and it also ends up favoring the peers who give it a better ROI, which is somewhat similar to BitTyrant. Now, a couple extra things to note here is that the download performance is quite good. So 60% median download time, so 40% improvement, and 70% of the downloads end up benefiting from using PropShare, and otherwise you don't suffer. You suffer negligibly whenever you don't benefit. Now, as for controlled populations, in this case, we ran experiment on Planet Labs. So this is a worldwide distributed set of computers where you can deploy whatever code you want. So we can basically emulate what might happen as there's many more peers contributing or using proportional share. So here's basically a setup of the experiment. We start off with all BitTorrent peers and slowly modify the population to all PropShare. Let's give you a quick overview of the results. What we ended up showing was that whatever the population is, the subpopulation of PropShare ends up outperforming the rest of the population of BitTorrent peers. And as we move from all BitTorrent to all PropShare ends up performing system-wide better. So system-wide, we get better system-wide download times than if everything was PropShare. So what this means, combining this result with the previous result, is that there's individual incentive to use PropShare, even now, regardless of what others are doing. And as everyone starts to do it, we get overall improvements to download times. So that finishes up with whom you should trade. It demonstrated that proportional share is a better auction. We can think of BitTorrent like an auction. Proportional share is an improvement. Let's return to this notion of what pieces of the file I should trade. What should I trade with those neighbors? And again, this notion of thinking of it like an auction gives rise to this idea that what it boils down to is how would I best advertise my auction? Nobody's going to bid in my auction if they're not interested in what I have. So how do we express interest? Well, BitTorrent does that by use of what's called a bit field. So bit field is simply an array of bits that represent which pieces of the file or blocks of the file the peer has. So in this case, this peer has block 0 and 1, but does not have block 2. Peers periodically exchange this information with one another. So the red peer sees that the green peer has something he doesn't, and vice versa. And so they tell one another, I'm interested, and this opens up the opportunity for them to start trading with one another. So if you imagine, there are various kinds of interest configurations that will be more or less preferable to a peer. So consider that I'm the red peer. The least preferable thing to me is that nobody's interested in me, but they're interested in everybody else. So they're progressing through the download, and I'm getting nothing. The other side of the spectrum, nobody's interested in anybody else, everybody's interested in me, and for anybody else to progress through the download, they have to be uploading to me as well. So that brings rise to our first goal, which is to be interesting. Now let's see what happens here. So here, again, I'm the red peer. I have the yellow and purple piece, and I have my two neighbors, the blue peer and green peer. And I'm in my ideal interest configuration. They're both interested in me, not interested in one another. The standard practice in BitTorrent, as you might imagine, is to simply truthfully state whatever pieces of the file you have. I don't want to state more than what I have, because if I do that, they might request something that I don't really have. They'll catch me as a cheater, and nobody will want to trade with me. So I'll state everything that I have, try to maximize my interest. The thing is, after I do this, these peers could request different pieces from me. And now I enter this intermediate interest configuration, one in which, sure, they're interested in me, but they're also interested in one another. Now, why isn't this as good as our ideal case? Well, because now they can trade with one another. They've effectively decoupled from me, and they can progress through the protocol without requiring me as sort of this middleman or some, the necessary peer in order to progress through the protocol. So we have this intermediate interest configuration, which again gives rise to our second goal, which is not only do I want to be interesting, I want to keep other people from being interested in one another. Now, how can I possibly go about doing something like this? Well, suppose I have this industrious peer here, and he decides, instead of stating exactly what he has, he's going to underreport. He's going to say, I just have the yellow piece. Now, why would he do something like that? Well, because now he's restricted what the blue and green peer can request. They both have to request yellow, at which point I then say, oh yeah, I also happen to have the purple piece. And so if they want to progress through the protocol, they have to continue coming through me. They get the purple piece. I maintained my ideal interest configuration that whole time. How did I do that? By strategically underreporting what I had. So while it doesn't serve you to overreport what you have, because you could be caught, it also doesn't necessarily serve you to report exactly what you should report. Really a surprising result. There's almost this weird inflection point where I have to state something, but the best thing for me to state is something that's not exactly the full truth. So this gives rise to several possible different strategies on how to underreport. Here's one example. When one of my peers loses interest in me, that's when I'm going to reveal to him that I have a block. What am I going to reveal? I'm going to reveal the most common block that I have that he does not have. Why the most common one? Well, I have to reveal something to this peer, and if I reveal a rare block, then he might gain interest in everybody. If I give him the common block, that's going to minimize the interest. There's a question.
Is the number of peers that you're communicating with so small here that there isn't sort of a cap of diminishing returns? I mean, at some point, you have your bandwidth saturated, and you don't really care if other people are trading with each other or not.
So the question is, why do we necessarily care if people are trading with one another? Isn't there enough to go around, right? Because we only have so much bandwidth. I'm going to show a result in the next slide that shows that improving this interest, maintaining this interest, can take you a very long way. So really, this comes at very, very little cost. And by maximizing the interest that people maintain in me, that's an excellent question. What are the performance gains? And we'll see that in just a second. So this question is, returning to this, when a neighbor loses interest, that's when I'm going to reveal the most common block I have that he does not have. So implemented this as well. So the prior results we had implemented in the Azurius client. These are also implemented in the Azurius client, a very popular BitTorrent client. And here's a result with one strategic revealer, this purple line here. Let me explain this plot real quick. The x-axis is the time into the download. The y-axis is the fraction of peers with mutual interest. That means of all the peers I'm interested in, what fraction of them are also interested in me? And where the lines stop is where the download has completed. So what we see is that the strategic underreporter reaches his peak interest quickly and holds onto it. And in so doing, ends up downloading the file significantly faster. So what this means is that peers have the incentive to strategically underreport. Let's take it to one extreme. What happens when everybody starts strategically underreporting? The downfall here is that peers start wasting time trying to figure out what the heck they actually have. Hey, I have piece 5. Yeah, me too. I have 6. Me too. 7. What about 107? You don't have that? Okay, great. We can finally exchange. So you end up paying these additional round trip times just to arrive at this truth. And in fact, we ended up seeing in our implementation a 12% overall increase in download times. So we looked at trying to incorporate this back into the auction model, and there may be ways to do that, but we ended up coming up a bit short. It seemed as though incentives weren't really solving this problem of underreporting. And I'm going to explain why. That actually this is sort of, you can think of this as a problem in security. So in the second half of the talk, I'm going to explain why incentives aren't necessarily the mechanism to solve this. There's other approaches instead. So to summarize real briefly this notion of applying BitTorrent or applying incentives to BitTorrent, we showed that economic theory can give insights into a protocol and can get us some very strong results, like our fairness property of the more you give, the more you get. But then incentives they do have their limitations. And that's what brings us to the second half of my talk. I'm going to talk now about the inconsistent representation of state and a design of a piece of trusted hardware. And this is work that I did while an intern at Microsoft Research 2 summers ago. And what this work seeks to address is a common tool, a tool that's very common between both selfish participants and malicious participants. And that's a tool called equivocation. What equivocation is, I can state it very, very simply. All it is it's sending 2 conflicting messages to 2 other participants. That's it. That's the attack. As you can imagine, since I can state it so simply, it can be very versatile, and it actually appears in many different kinds of systems. So the classic example, the place where many people have considered this notion of equivocation, is in the Byzantine generals problem, where the idea is that an attacker, a Byzantine faulty node, could tell one of his colleagues, advance, and tell another colleague, retreat. So equivocated by sending 2 conflicting messages to 2 different participants. This is one example. It's kind of a nice theoretical example. You can even think of this in terms of data centers. For example, yes, process this user's transaction. He's just bought this book. And then I actually tell another server, do not process this user's transaction. There's still more to sell, which causes many, many different kinds of problems. Has some nice real-world application. But this is just a couple examples. We considered many, many more. Let me go through a couple more. Voting, for example. I can equivocate in voting by telling you I've counted your vote and then subsequently reporting a tally that doesn't include your vote. In the context of BitTorrent, I can equivocate by telling one peer that I have a piece of the file and subsequently tell another peer that I don't have a piece of the file. And there are just a few examples. We see it in many, many different areas. For instance, in DNS, in DHTs, in auctions, many, many different areas. It's a very versatile basis for an attack. It's also extremely powerful. Now, to demonstrate just how powerful it is, I think the best example has us returning back to the Byzantine generals problem. And if you recall, if you had F malicious users who were Byzantine faulty and could do anything, then we need 3F plus 1, a 2/3 majority of good users, non-faulty users, in order to achieve consensus. But there's a recent result by Chun and others which showed that if peers just couldn't equivocate, they could do anything but equivocate, then you only need a simple majority. This is really a fascinating result. It would seem to indicate that the crux of the difficulty of Byzantine faults really comes down to this ability to equivocate. So what can we do about that? How can we make equivocation impossible? Well, so there's a proposal to use trusted hardware for this. And the idea was that we could make equivocation impossible by the use of trusted hardware. Now, what's really fascinating about this is it represents a new design space. So I talked about how we had these 2 different kinds of models. One where we could assume the altruism or the cooperation of everybody in the network, and one where we assumed that nobody was cooperative. But what this allows us to do is have an intermediate point, a point in which everybody is, for the most part, untrusted, except for one small piece of trust. So the idea is, can we put a small amount of trust in all of the participants and try to leverage that tiny amount of trust in order to get them to have overall system-wide trustworthy or at least provable behavior. Now, if you consider what's the ideal deployment for this kind of trust scenario, the ideal deployment would be one in which it was ubiquitous, where everybody could be trusted a tiny little amount, supposing that we can leverage that trust to get something done. And if we want to be ubiquitous, then practically speaking, it has to be small. Why is that? For a few reasons. One, ubiquity can only come at low cost. If we want this deployed in many, many machines, just like the Trusted Platform module, the TPM is deployed in many machines, a primary design decision has to be the cost in building this. So it has to be functionally small to achieve low cost. What's more is if we want these to be tamper resilient and we want to be able to prove something about our trusted computing base, those become much easier and much more cost-effective the smaller it is. So this gives rise to the following question. What is the minimal abstraction necessary to make equivocation impossible? What's the smallest amount of trust we can assume or require in order to make equivocation impossible? You could imagine, for instance, having a whole Turing machine, a whole trusted Turing machine on every host. You could even imagine getting a little bit smaller, maybe a trusted log on every single host. So we'll go a little bit further. I'll just kind of finish the steps for you. It turns out that all that we need to make equivocation impossible is a counter. A counter and a little bit of crypto is enough trust on these hosts to render equivocation impossible. And this is effectively, these are the fundamental components of TRINC. So TRINC stands for trusted incrementer, consists of two things, a monotonically increasing or non-decreasing counter, and a key used for signing. So this is a TRINC, a trusted incrementer. 34 right now is the counter value, and it has a key K. And it outputs attestations which bind some user data to a counter value. So the form of this attestation right here is bind this data, called data, to the number 36. So what does TRINC do? Here's the abstraction. It looks first at this number. Is this new counter value no less than the current counter value? That is. So we'll update the counter value, and we'll output the following attestation. Consists of the old counter value, 34, the new counter value, 36, the data that the user is trying to bind this to, all signed with this key K. Now, if you think about it, there's fundamentally two different kinds of attestations. Basically, one that moves the counter forward or one that doesn't move the counter forward. We just can't move the counter back. The attestation that moves the counter forward we call an advance attestation. And what that means is that we've advanced that counter, and so data is intrinsically and forever bound to the number 36 in this case. Another thing to note here is that there was nothing bound to 35. Since we never moved up to it and we moved past it and we can never move back to it, nothing can ever be bound to 35. This is the kind of attestation that's going to make equivocation impossible. Because if you can see that, because I can only move up to 36 once, there's only one attestation, one thing I can bind to the number 36, and that's the only thing I'll ever be able to give out. I'll never be able to move up to 36 twice. I can't equivocate. The other kind of attestation is a status attestation, is what we call it, one which does not move the counter value up. And what's nice about this is it allows us the ability to ask another participant, what's the current counter value that you have right now? So what I do is I would provide a nonce to you, and you would reply back with an attestation to that nonce without moving the counter up. And what you're saying is, at least at the time that you generated that attestation, there's nothing beyond 36. Nothing has been bound to anything beyond 36 as of yet. So a few practical considerations. So that was the abstraction. How do we implement something like this? What are the concerns in implementing this? And the first is that oftentimes one incrementer is not enough. We may have multiple systems running on the same machine, and there may be some complex systems that benefit from having more than one counter. For example, consider the example of trying to maintain your account balance. As nice as it would be to have a bank account that constantly was monotonically increasing, unfortunately, there are some things that we have to buy. We can't always find free food, even at college campuses. So imagine then we could implement this with two counters. One counter that represents all of the money I've ever made, and another counter which represents all of the money I've ever spent. And then the difference is simply my current balance. So the actual trusted component that we want was going to have multiple counters, and this component is what we call a trinket. So trinket consists of one or more trinks, trusted incrementers, and also has an API that supports this trinc abstraction. So it has, of course, the attest call that I showed in the previous slide, and also has various calls to allocate counters, to free counters, to also even handle certain things like power failures, for example. And the thing is, these are some extremely hard problems. Coming up with the right API for this. I mean, finding the minimal abstraction is also a remarkably difficult problem. I'll demonstrate why it is the minimal abstraction to some extent, or what we can do with it. But consider for a second this API of allocating and freeing these counters. If we don't do it just right, you could force the counter up really high, free that counter, allocate a new one, start it over, so on and so forth. So we have various things in place to make sure that you can't do this, that basically each counter gets a different ID by effectively, recursively using trinc, by using something called a meta counter. So every counter has an ID given out by a counter that uniquely identifies them. So I won't go into any more detail other than that very high-level view of the rest of the API. Instead, I'd like to go a little bit further in terms of describing how we could go about using this abstraction of trinc. So I'm going to talk about a few different applications. I'd like to start off by closing this loop that I opened up in the first half of the talk, which is this problem of peace underreporting in BitTorrent. So you might ask yourself, why is this even equivocation? This peer, this selfish peer, said the same thing to both of these peers. He said to both of them, I only have the yellow block. So to see why it's equivocation, take a step back in time with me, way back to when this peer obtained this purple piece from this purple peer. When he obtained it, he acknowledged receiving this, and then subsequently ended up saying that he only had the yellow piece, effectively telling one peer, I have received the purple piece, and telling another peer, I've never received this purple piece. That's where the equivocation comes from. So how do we solve a problem like this? We've identified equivocation. How do we solve it? And there are a few questions to ask when applying Trink. The first question is, what does the counter represent? We want it to be something that naturally increases. So in this case, it's going to be the number of pieces that I've received throughout the download. To what should I attest? Well, again, it should be tied to this, to the counter value. So it's going to be the bit field, the pieces, that array that represents what pieces of the file I have. And also, it's going to be the most recent piece I received. And I'm going to demonstrate why we need to do that. Last, when do I attest? When do I need to make sure that I'm moving my counter forward every time I receive a piece? When am I going to give out a status attestation? Well, whenever anybody asks for one. We could be progressing through the protocol at different speeds. So if you want to see what I've gotten since the last time we've spoken with one another, you can just ask for a status attestation, and I'll send that to you, and you'll at least be able to see how many pieces I've received. So let's take a look at how we can modify BitTorrent, what attestation we're going to add to ensure proper reporting of the pieces that we have. So suppose we're the red peer, and we receive a yellow piece. The attestation I give to the yellow peer is the following. I'm going to give it the counter value 1, because that's all the pieces I have. I say, here's the bit field I have the yellow piece, and the most recent piece I received is yellow. So as more pieces come in, we continue doing this, we return these attestations, and the peers who receive them check two things. They check that the counter matches the size of the bit field, which in this case it does, 1, 2, 3, and they check to make sure that this peer has been attesting to the most recent piece, which again, this peer has been doing. And as a result, this peer has consistently been telling the truth at each step in the protocol. Now, why do we attest to the most recent piece? Suppose that we didn't. Suppose that instead, all we checked was that the counter matches the bit field size and that the piece that I uploaded to you is in the bit field. Here's an attack we could do. I get the yellow piece, I return the proper attestation. I get the purple piece, I wait. I get the blue piece. Now I form one attestation that's going to satisfy purple and blue of the following form. I have purple and blue. My counter value is 2. They check that the counter matches the bit field size. It does. They check to make sure that their piece is in the bit field. It is. So it looks good to them. But of course, this peer is underreported. He's equivocated by telling some peer that he has the yellow piece and telling other peers that he hasn't received it. The lesson learned here, yes, question.
I was going to ask, on the previous slide, you talked, now you've serialized the piece exchange. So does that make the practical network nature of BitTorrent, in which you're concurrently trading with multiple peers, does it complicate those kinds of issues and potentially reduce like pipelining current transmissions? So
the question is, now that we're serializing these exchanges of these attestations, are we hurting the parallelization? I would argue that we're not. So these are effectively going to be the have messages, or effectively like the acknowledgement of having received the piece. In the background, we can be requesting these attestations. So I don't see that it would affect it. And we have implemented this, and it hasn't seemed to affect it. So there's just sort of this background process of almost like pinging periodically, like, hey, did you get any more attestations? Did you get anything? But it ends up piggybacking on existing messages. So the lesson to learn here, the reason why we need to attest to the latest piece, is the following. Notice that if the purple or blue peer had seen that first attestation, they would have seen that attestation where we attested to receiving the yellow piece. We would have seen that we didn't have the whole picture. The lesson here is that if we don't have the full log, we have to ensure proper behavior at every step. So these are just a few examples of what Trink can do. I presented 2 of them. Here are some more different ones. We go into some more detail in the paper, and in fact, that was an important part to the design of Trink, was iterating on multiple different application domains. So to summarize my talk as a whole, I presented some various means of achieving incentives in the context of BitTorrent to achieve consistent and truthfulness from users, from even selfish users. I presented our design of Trink, a trusted component, to assure consistency from selfish and malicious users. I demonstrated that neither one of these mechanisms is enough, and that if we put the user first, then perhaps in the future we can indeed achieve systems with cooperation. Thank you for your time, and I open to your questions.
So I think we've got a time for a question or two, if there's some more. Let me fire one off, and then I think we'll go next. So one of the things that is most curious to me about Trink is you've been able to show that you're able to emulate some existing protocols with it. Have you found the boundary of what a trusted counter is able to do? Are there examples of trustworthiness properties that we can do that we don't know how to do with just a counter and a key?
So whenever we can boil it down to a problem of equivocation, that seems to be something that it can indeed solve. So when it does come down to sending two conflicting messages, as soon as you get past that, so for instance, if consistency isn't the issue, but truthfulness is the issue, then that's where assuring this consistency will not be enough for this. So that's where I think BitTorrent is kind of this nice example where you have the incentives getting somebody to tell the truth just once, and consistency making sure that they want to tell the same view to everybody. And when you merge those two together, as soon as I can get you to want to tell the truth once, I got you telling the truth to everybody from then on. Perfect. Great. Thank you very much.